Deduction of Hamilton's equations from modified Hamilton's principle or variational principle. Deduction of Hamilton's equations from modified Hamilton's principle or variational principle. So here let us consider a phase space, and we have to express at constant time the coordinates qk and pk. Here we have to express the delta variation, that means very small variation of the coordinates qk and pk. We have to express in terms of a parameter alpha, which is common to all the points of the path of integration. Let me say once again, let us consider the phase space, and here at constant time we have to express the coordinates of qk and pk. The delta variation of these coordinates we have to express in terms of parameter alpha, which is common to all the points of the path of integration. And here we have a similar equation. Let me say here it is not there. So delta y equals to dou y by dou alpha into delta alpha, which is equals to eta x delta alpha. I will tell you once again the equation. Delta y equals to dou y by dou alpha delta alpha, which is equals to eta x delta alpha. So similar to that equation, we are considering here the delta variation of these two coordinates. So delta qk, delta pk, we have to express in terms of the equation which I have said now. So delta qk equals to, just we are replacing qk, we are replacing with qk in the place of y. So delta qk, which is equals to dou qk by dou alpha into delta alpha, which is equals to eta k delta alpha. And another coordinate, so delta variation of pk, delta pk equals to dou pk by dou alpha delta alpha, which is equals to eta dash k into delta alpha. So this is the equation, and here we have eta k, eta dash k. These two are the arbitrary. Eta k, eta dash k. These two are the arbitrary subject to the conditions. So here we have the conditions: eta k at time t1, eta k at time t2 equals to 0, and also eta dash k at time t1, eta dash k at time t2 is equals to 0. So here these eta k, eta dash k. So here we have the conditions at time t1 and time t2. These values equals to 0. So therefore delta variation of the integral. So here this is the modified Hamilton's principle. So this is the equation, modified Hamilton's principle, which is delta integration t1 to t2 sigma k pk q dot k minus h into dt, which is equals to. So here we can expand this equation. So delta integration t1 to t2 sigma k pk q dot k minus h into dt. So we will expand this one. So first let us expand by using delta pk q dot k, and delta h we have to expand, and here we are expressing at constant time in terms of parameter alpha. Already we have given the statement here. We have to express these delta variation coordinates at a constant time in terms of parameter alpha, and these are common to all the points of the path of integration. So based on this one, so let us multiply and divide with delta alpha. So here we have multiply and divide with delta alpha, dou alpha here for these two terms, and we have multiplied, we have take common, and we have wrote here. Now let us see here. So delta pk q dot k. So here pk q dot k, it is in the form of u derivative of uv. So u derivative v plus v derivative u. So by using that formula, so here we are, so here dou pk into q dot k. That means here u is q dot k, v is pk. So q dot k into dou pk by dou alpha plus pk into dou q dot k by dou alpha into delta alpha. So here we have expanded this one in terms of u derivative v, v derivative u, and we have multiplied and divided with dou alpha for these two terms, and we have taken common, and we have wrote here delta alpha. Now we have to expand, so delta into h. So delta h, and we are multiplying with dou qk and dividing with dou qk. simultaneously we are multiplying with delta alpha, multiplying and dividing with delta alpha. So here we have considered the coordinates qk and pk and expressing in terms of alpha. So here dou h into multiplying dividing with dou qk, multiplying and dividing with dou alpha. And here also with pk, multiplying and dividing dou h with dou pk and dou alpha. So here we have expanded this term and into dt. Now see, so here we have taken common, uh, overall we have to take common this delta alpha. So here for each and every term we have delta alpha. So let us take common as delta alpha integration t1 to t2 sigma k. And here initially we have here eta k equals to dou qk by dou alpha, and we have eta dash k equals to dou pk by dou alpha, and we have to replace dou pk by dou alpha, dou qk by dou alpha with eta k and eta dash k. So here we have the terms dou pk by dou alpha. So here we have to replace with eta dash k and dou qk by dou alpha. So here we have dou qk by dou alpha. We have to replace with eta k. So here we have to replace with dou pk by dou qk with eta dash k, and here we have to replace with dou qk by dou alpha with eta k. So we have to replace, and here dou pk by dou alpha with we have to replace with eta dash k. So by replacing the terms with eta dash k and eta k, we'll obtain this one delta alpha integration t1 to t2 sigma k eta dash k q dot k plus pk dou q dot k by dou alpha minus eta k dou h by dou qk minus eta dash k dou h by dou pk into dt. So here now let us consider this term. We will solve this term. We will pk into integration t1 to t2 pk dou q dot k by dou alpha. Let us consider this term and we will expand this term. So integration t1 to t2 pk. We have q dot k. Q dot k means d by dt dou by dou alpha into qk. So here now this is in the form of integration uv. So this is in the form of integration uv. Now we will expand this term. So we have integration uv equals to u integration v minus integration q dash integration v dv. So by using that integration uv, we will expand this term. And before we are expanding into integration uv, let us replace dou qk by dou alpha with eta k. Already just now we have seen dou qk by dou alpha, we are replacing with eta k. Now we will expand pk into u into v. So integration uv. So this is in the form of integration uv. Let us expand this one in terms of integration uv. So if we expand this one into integration uv, we will obtain pk comma eta k integration limit over t1 to t2 minus integration t1 to t2 p dot k eta k into dt. So here already we have a condition. If you apply these t1 t2, if you substitute this in the limits, so eta k at t1 eta k at t2 already we have 0. So eta k at time t1 eta k at time t2 0. So this term becomes 0. So we will remain only this term. So minus integration t1 to t2 p dot k eta k into dt. And also in the view of modified Hamilton's principle, already this equation we have seen, the delta variation of the integral must be 0. So therefore here that means if you see this becomes 0 according to that condition, this becomes 0. So this will remain. So if this is 0, all this equals to 0. So just we will replace, just we will write that equation. So based on this one, so in the view of the modified Hamilton's principle, delta variation of the integral must be 0. So therefore, so we will replace this term. Now let us see. So here if you consider this one, just we have to replace pk delta dou q dot k by dou alpha with minus integration t1 to t2 p dot k eta k into dt. And if you replace this term with this term, here we will obtain eta k. In each and every term, we will obtain eta k in two terms and eta dash k in two terms. So we have to take the common as eta dash k and eta k. So by substituting, by replacing this term with this term, we have to take common eta k and eta dash k. Let us see. Here we have replaced the term and we have take common as eta dash k and eta k. So already I told you this becomes 0. LHS becomes 0. So in the view of modified Hamilton's principle, so delta variation 0 means, so LHS, here we will have LHS equals to 0 means this term becomes 0. So here 0. So integration T1 to T2. So here we have eta dash k into delta alpha, which is dou pk. In the first we have, see here. So delta qk equals to eta k into delta alpha. So eta dash k delta alpha equals to dou pk, delta pk. So we will replace eta dash k into delta alpha with delta pk and eta k delta alpha with delta qk. Let us replace here. So here already we have taken common. So eta dash k into delta alpha, which is equals to delta pk, and eta k into delta alpha, which is delta qk. Just we have to replace these two terms. So integration t1 to t2 sigma k q dot k minus dou h by dou pk into delta pk minus p dot k plus dou h by dou qk into delta qk into dt equals to 0. So here we qk and pk, the coordinates, these two coordinates are independent variables. They does not depend on anything. So here these two are independent variables. So integral will become 0 when this one equals to 0 and this one equals to 0. That means because of these two coordinates are independent, the integral when this equals to 0 and this will be the integral will be 0 when this term equals to 0, this term, that means quotient of delta pk equals to 0, quotient of delta qk equals to 0. So q dot k minus dou h by dou pk equals to 0, p dot k plus dou h by dou qk equals to 0, or q dot k equals to dou h by dou pk, p dot k equals to dou h by dou qk. So these are the desired Hamilton's canonical equations. Thank you.